Good morning, welcome to Algebra 2. We are looking at lesson 9.3a. Now, there's a typo on the homework assignment. Turn to page 2 of your lesson. In the lower right, it says the homework section 9.2. Cross off the 9.2 and write 9.3a. The homework due on Friday is 9.3a. Let's go to page 1. We're looking at rational functions. Now, the graphs of rational functions tend to have this hyperbolic shape. Rational functions have a shape that looks like this two-branched graph, and in general, a rational function is any function that is a ratio of polynomials. We looked at polynomials earlier in the course, so polynomial p of x divided by polynomial q of x would be a rational function. Notice p of x and q of x are defined as polynomial functions, except we can't allow the denominator polynomial to equal 0, otherwise we'd have division by 0. Now, here's some big words regarding points of discontinuity. And I think the handout itself is kind of making fun of itself by giving you all these big words and saying, what? Okay, misspelled that. It should be W-A-C. What is the response that some students have to statements like, if a is a real number for which the denominator of a rational function f is 0, then a is not in the domain of f. As a result, the graph of f is not continuous at x equals a. Also, the function has a point of discontinuity at x equals a. So apparently, whoever made up this lesson was like aware of the fact that students would look at this jumble of big words and respond with, what are we learning today? So let's take a look at it in terms of the basics. A discontinuity, there's only 3 types. Sometimes the discontinuity is a hole. Sometimes the discontinuity is a vertical asymptote. Hi. Oh, Mason is absent. So we've got a vertical asymptote is a discontinuity, and a jump. Now we've already seen jumps in this course when you do a piecewise function, like maybe you have in first semester of this course you'd have like a parabola for a while, and then maybe it jumped down to the square root function. So it's a child of x squared as one piece, and another piece might have been a child of the square root of x. Well, we call that a discontinuity of jump. Now, the movie Chappaquiddick that just came out 6 days has to do with a car driving on a road in the key scene. And if you're building a road, you want to make sure that it's continuous. You don't want discontinuities in the road. Suppose there's a hole in the road, just like sometimes in the graph of a rational function, you sometimes have a hole. Imagine what would happen if you're walking on this road. Here's a stick figure of a person walking on the road, and here we go. They're walking along the road, and then, oh, there's a hole. Now what's happening? Now we're falling forever. Now, falling forever isn't that bad while you're falling, but it's tough psychologically. It's like, wait a second, how long can this go on? You know, something bad could happen pretty soon. So you don't want to have holes in the road. It's called a discontinuity. In the movie Chappaquiddick, it's a story about one of Joe Kennedy's 4 sons. Well, one of Joe Kennedy's sons became president. JFK got assassinated, so he died. Then Robert Kennedy got assassinated. And then another Kennedy's son died. So the last one was Ted Kennedy. And Ted Kennedy was a senator back in 1969 when he was out on a region of Martha's Vineyard called Chappaquiddick. And it was the same weekend that Neil Armstrong was walking on the moon. You see, JFK said, hey, let's send a man to the moon. This was in the early 60s. So by 1969, Neil Armstrong was finally ready to walk on the moon. He walked on the moon the same weekend that JFK's brother was driving on a road in Chappaquiddick, and the car went off the road. The car did not fall through a hole in the road, it just drove off the road. Now, the story of what happened after the car left the road and landed in a body of water is one you might want to watch in the movie Chappaquiddick. Now, the first thing that Senator Ted Kennedy said when he came out of the car was, quote, "I'm not going to be president," unquote. Sure enough, he did not win the 1972 presidential election because of the story surrounding what happened when he went off the road. So it wasn't a discontinuity in the road, he just went off the road. I don't know what his blood alcohol level was. No one measured it as far as I know. But discontinuities in roads can cause problems for cars that are driving along the road. Also, imagine that you're driving on a road in which your road hits a vertical asymptote. Now, if you're driving along the road, or suppose you're walking on a road and then the road approaches the vertical asymptote, you have to go uphill an infinite distance to get beyond the vertical asymptote. So, if you're an engineer, you want to avoid discontinuities in your graph. It's not unusual to use the graph of a rational function or some sort of polynomial function to help you design your road. I mean, that's why we're teaching math in high school, is because we realize some people are going to become engineers and they might need to use these functions in designing things like roads. So, the bottom line is that what you need to know for finding the locations of these discontinuities is that you're going to have to find values of x and they've got to be real numbers. If you find a value of x and it turns out that it has I in it, a non-real number, the square root of -1, then ignore those. That won't correspond to a discontinuity. Find values of x, they've got to be real values of x, that cause the denominator to equal 0. Then you have located the discontinuities. There's 3 types of discontinuities that we're going to be locating: holes, vertical asymptotes. We've already done jumps back in piecewise functions. Today we're looking at holes and vertical asymptotes. Let's do our first example of how to find points of discontinuity. We will talk about whether it's a hole or a vertical asymptote later, but for now, the first move is to factor. In the numerator, we're going to factor a 2 out of 2x minus 6, leaving x minus 3 in parentheses. When you factor an x out of the denominator, what's left in parentheses? Jonathan? When you factor in x out of the
x plus 5.
X plus 5 is left in parentheses. So what we have to do is watch out for any values of x that make the denominator equal 0. Well, set the denominator equal to 0. X times x plus 5 equals 0. And you can tell, based on the zero product property, that there's going to be 2 values of x that make the denominator equal to 0. If x is equal to 0, then the denominator will be equal to 0. That's one solution. And if x equals -5, then the denominator is going to be equal to 0. I mean, think about it. Replace both x's with -5. You get -5 times 0, that's 0. Also, if you put a 0 in for x, you get 0 times 5, which is also 0. Any questions on how to find the values of x? So when they say any points here, what they really want here is the values of x, where we have discontinuities. All right, let's go to part B. Factoring 4 out of the numerator gives me 2 minus x. Go ahead and factor the denominator on your own. It's good review of factoring from semester 1. Factor the denominator. Need 2 numbers that multiply to -12 and add up to -4. What are they? What are those 2 numbers that multiply to -12 but add up to -4? Oh my goodness. Bethany, what would you say there?
6 and 2.
Now, positive,
-2.
oh, positive 6, -2, let's find out.
Oh, it's switched.
So what should the two numbers be?
The general objective is -6 and 2.
So -6, positive 2, so sure enough, 2x plus -6x is -4x, we got it. So, go ahead and finish the problem. Find all the values of x that cause the denominator to be equal to 0. When you're done, take a peek up here, see if we agree. I've got the answers circled in red. So, next we need to find out, what does letting x equal 6 do to the graph? Does that cause it to have a vertical asymptote or a hole? Well, let's find out on the next page. So, the holes occur if the factors cancel. Vertical asymptotes occur when you just have a 0 in the denominator. Just ignore imaginary numbers. Those will show up in some cases. So these are the terms we need, hole and vertical asymptote. So here we go, letter A. In fact, you know what, since we haven't seen any factors cancel yet, let's actually start with letter B, then we'll go back and get A. What we mean by factors cancel, they give you the key information up here. A hole occurs if factors cancel. So on the homework solutions, which are already posted, you'll see that I cancel the factors in yellow highlights. So the x plus 2's cancel. Therefore, this is the graph x minus 4 over x minus 2. But it has a hole where x minus 2, or x plus 2 is equal to 0. So x plus 2 equals 0 gives us a 0 of -2. That's going to give us a hole in the graph. Now, there's another expression in the denominator that could equal to 0. That's x minus 2. That equals 0 when x equals 2. So if this were a homework problem, you would say, well, at -2, we've got a hole, but when x equals +2, we have a vertical asymptote. And we need to take a peek at the graph on the graphing calculator to see if we can learn how to use our graphing calculator to verify our answers, because sometimes you're on a part of a test where a calculator is allowed. Not very often, but occasionally you're allowed to have a calculator with you. So let's see what a hole looks like on the graph. What does a vertical asymptote look like on the graph? So we're going to go to the y equals menu. And it's not the easiest thing to type in the original equation. I typed it in for first period, but I'm going to type it in again. Since the numerator has two factors, I'm going to use a double left parentheses before typing x minus 4 times x plus 2. Double right parentheses means I've completed the numerator. Now, I'm going to open the denominator with another double left parentheses, giving me x minus 2 times x plus 2. Okay. My viewing window, -10 to 5, that should be fine. Notice what this graph has. According to our analysis, there's supposed to be a hole at x equals -2 and a vertical asymptote at x equals +2. Well, it does seem plausible that there would be a vertical asymptote at x equals +2, but I don't see a hole in the graph here at -2. Well, look at what happens when you try to trace -2. Trace -2 gives you a y coordinate. If there's a hole there, there's nothing there. So if this were, if we're sketching the graph, which we're actually going to be drawing these graphs in tomorrow's lesson, we'd actually draw a hole in the graph right there. So I'm just going to pull this in to our document. So just to quickly summarize how it is that the calculator really does agree with the work that we did with paper and pencil. So yeah, this will be nice for the notes that I post online. just be able to see it right here. There really is a hole in the graph when x equals -2. Golf ball -2 leaves a hole in the graph. And there really is a vertical asymptote at x equals +2, according to the graphing calculator. Now, notice how let's swing back to letter A. In letter A, there is no cancellation. There's no factors in the denominator that match up with factors in the numerator. Over here, there was a match, so they canceled out. So here, there are no holes in the graph. X equals 3 and x equals -4 are both points at which we have vertical asymptotes. So really, as you can tell, there's not much work involved in these homework problems. You just have to find the values of x that make the denominator equal to 0. I think the answer to example 2a is x equals 3 has a vertical asymptote, and x equals -4 also has a vertical asymptote. Any questions on how to tell whether the zeros of the denominator are going to lead to vertical asymptotes or holes? Because each zero of the denominator has to be categorized as either associated with a discontinuity that's a hole in the graph or vertical asymptote. Now, if there had been, okay, so it turns out that Ted Kennedy, when he was a U.S. Senator, he was driving in Chappaquiddick, drove off the road into the water. There was a woman with him in the car. She did not survive, and that's why many people figure, well, if she had survived, then maybe he could have become president. Everyone wanted him. A lot of people wanted him to become president in '72. He was next in line. He probably would have had it not been for driving off the road. He actually left the scene of the accident, just left her down there. She's underwater, she's in the car, trapped. He's out of there, mourning over the fact that he's just not going to be president. I'm not going to be president. I've just ruined my life. Well, he ended up still being a U.S. Senator. But he changed U.S. history, according to some who analyze U.S. history, and the effect of Chappaquiddick on the list of people who became president of the United States. So, if there had just been a big hole in the road and he would have fallen through the hole, he probably still could have been president, because then it's not his fault. Driving into a hole is just fine if you want to become president. Driving off the road with a significant blood alcohol level, that's a different story, friends. Driving a hole is all you want if you want to
What
become
if you drove
president.
into the whole drone too?
Well, see, if they find out that you're drunk when you drove into the hole, then that could be a problem. Let's go to the next example, part C. Now, in part C, the numerator is not yet factored. This is some good factoring review. The difference of squares factors into x plus 1 times x minus 1. And the denominator is already factored for you. There's no guarantee that the denominator will be factored for you ahead of time, but it was this time. So, notice the x plus 1's cancel. So would you please categorize each value of x that makes the denominator equal to 0 as leading to either a vertical asymptote or a hole. So for all three of them, 0, -1, and +5, write either hole or a vertical asymptote under each one. I mean, my advice to teenagers is usually to not drive your car into a hole. Although I had a friend in high school who did exactly that. There was some construction going on, hole in the road, drove his car right into it. But he survived to tell about it. Okay, x equals 0, what's that one gonna be? So Mia, would you say there's gonna be a vertical asymptote or a hole here?
How do you?
Well, it's always gonna be a vertical asymptote unless it came from canceled factors.
Oh, so.
Yeah, vertical asymptote, VA for vertical asymptote. How about x equals -1? Is that gonna be a hole or a vertical asymptote there? Thomas?
Hole.
There's gonna be a hole because it came from canceled factors. That's what they mean right up here. A hole occurs if factors cancel. If factors cancel, then the zero of the canceled factors are the x-coordinate of the whole. All right, so there's one whole, two vertical asymptotes. Try letter D on your own. Categorize each point of discontinuity as either a vertical asymptote or a whole, if there are any. X squareds, I don't know if you think the x squareds cancel or not. They don't. The 9s also do not cancel. Can this thing be factored? What's the factorization of x squared plus 9? Does anyone remember what that is? What's the factorization, the factored form of x squared plus 9? Who's got it? Owen.
X plus 3 squared.
X plus 3 times x plus 3. Nice try. It's not correct, because when you do the FOIL method, you get x squared, outers and inners give you 6x plus 9. It doesn't match up. It turns out that you cannot factor x squared plus 9. It's prime, cannot be factored. And therefore, there's if you just take the denominator, set it equal to 0, x squared plus 9 equals 0, you get x equals plus or minus I times 3, or 3i. It's plus or minus 3i. Plus or minus the square root of negative 9 gives you plus or minus 3i. So we got two zeros, x equals 3i, x equals negative 3i. Whole, vertical asymptote, what's going on? Neither. You just cross them out because they're not real numbers. It says right here in the notes, imaginary numbers are not points of discontinuity. So if there's an I in your 0, then ignore it. It's neither a horizontal asymptote, so the big answer here is none. There are none. Now, it's time to get going on the test correction, so I will hand your test back to you. And then after you find out how many problems you missed, you can pick up the test correction sheets. Take as many as you need.